The story of Max Planck's discovery begins long before his own experiments in a world of scientific confidence and philosophical certainty. The late 19th century was a golden age for physics. Newton's laws had reigned supreme for over 2 centuries, describing the motions of planets, pendulums, and particles alike. The universe seemed mechanical, predictable, and absolute. Scientists of the era believed they were on the verge of completing the great puzzle of nature. Some even declared that physics was nearly finished, that all that remained was to refine the measurements. But beneath this confidence, something unsettling was beginning to stir. In laboratories across Europe, strange experimental results began to challenge the very foundations of classical physics. It was in this moment of quiet chaos that the seeds of the quantum revolution were sown, a revolution that would one day be led by a man who never sought it, Max Planck. Before Planck, the physical world was seen as a smooth, continuous fabric, one that could be understood entirely through the laws of motion and energy. Thermodynamics and electromagnetism seemed to fit together perfectly, painting a picture of harmony between matter and energy. But then came an unsolved problem, deceptively simple, and yet deeply mysterious. How do objects emit radiation when heated? Every object, from a piece of metal to the stars in the sky, glows when its temperature rises. The color of that glow changes with heat, from dull red to brilliant white, and the intensity of the light varies across different wavelengths. This was known as Blackbody radiation, and understanding it became one of the most important challenges in physics. A blackbody is a perfect absorber and emitter of radiation, a theoretical object that doesn't reflect or transmit light, but emits it purely based on its temperature. When scientists tried to measure the energy emitted at different wavelengths, they obtained a curve that classical physics could not explain. The equations predicted that at shorter wavelengths, especially in the ultraviolet range, the emitted energy would increase without limit. This absurd result was called the ultraviolet catastrophe. It was as if the simplest object in the universe, a piece of heated matter, was mocking the precision of science itself. Something was missing, something fundamental that no existing law could explain. In Germany, at the University of Berlin, Max Planck watched this crisis unfold with a mixture of fascination and frustration. A quiet, methodical thinker, Planck had built his career on the laws of thermodynamics and the principle of energy conservation. He respected classical physics deeply, believing that the universe operated according to exact and deterministic rules. He was not a rebel, he was a savior of order. Yet fate demanded that he become the very force that would disrupt it. As Planck studied the problem of blackbody radiation, he found himself caught between two worlds, the precision of mathematics and the unpredictability of experimental results. By the 1890s, several scientists, including Wilhelm Wien and Lord Rayleigh, had proposed formulas to describe blackbody radiation. Each theory worked only for certain wavelengths, but failed miserably elsewhere. The equations of Rayleigh and Jeans, based on classical electromagnetism, predicted infinite energy at short wavelengths. Wien's formula fit experimental data at high frequencies but not at low ones. The situation was desperate. It was as if nature was playing a riddle, hiding its answer behind the limits of human understanding. And in the midst of that confusion, Planck decided to take a different path, not guided by philosophical beauty, but by the raw demand of fitting experimental truth. Planck approached the problem not as a radical, but as a mathematician seeking harmony. He believed that by refining the equations of thermodynamics, he could restore order to physics. But the deeper he went, the more he realized that the classical picture was breaking apart. The continuous flow of energy assumed by all physicists failed to describe the data. In a moment of profound insight, Planck did something extraordinary. He allowed himself to imagine that energy might not be continuous after all. To make his equations match the observations, he proposed that energy was emitted in discrete packets, proportional to the frequency of radiation. It was an idea so revolutionary that even he struggled to believe it. At first, Planck viewed his new formula as a mere trick, a mathematical convenience, rather than a statement about reality. He didn't yet understand what it meant, but the results were undeniable. His equation perfectly described the blackbody spectrum. It solved the ultraviolet catastrophe, matched experimental data, and restored sanity to physics. Yet beneath that success lay an earthquake that would shake the very foundation of science. The universe was no longer smooth and continuous. It was quantized, built from indivisible packets of energy. But before this new understanding could dawn, there was chaos, intellectual, emotional, and philosophical. The scientific world, so certain of its classical laws, now faced an anomaly that couldn't be ignored. The crisis wasn't merely about numbers, it was about the nature of reality itself. If energy came in discrete quanta, then light, heat, and even matter might not behave according to the comforting logic of Newtonian physics. This wasn't just a problem of equations, it was a problem of worldview. Planck's discovery emerged not from rebellion, but from desperation. The era before his theory was one of paradoxes and contradictions. Scientists could measure radiation with precision, but could not explain it with theory. Classical physics, once seen as perfect, began to show its limits. The gap between experiment and prediction grew wider with each discovery. Every new measurement seemed to whisper the same unsettling truth, that the old laws of nature were incomplete. Yet few could imagine what would come next. In those days, the laboratory was a battlefield of ideas. Instruments glowed with the light of heated filaments, spectrometers recorded the delicate dance of colors, and notebooks filled with data that refused to make sense. Physicists debated fiercely about the meaning of it all. Some believed that the anomalies would disappear with better measurements, others suspected that a deeper mystery lay beneath. The air was thick with anticipation, and yet no one could see the storm approaching. Planck himself was a man torn between reason and revelation. Trained in the rigid discipline of classical thought, he resisted the temptation to leap into speculation. But his mathematical instincts told him that the existing theories could no longer hold. He began to think about energy not as a continuous wave, but as something granular, like sand scattered across a beach, each grain small, but collectively forming the whole. He had no proof that this was how the universe worked, he only knew that his formula fit the facts. And for Planck, that was enough to present it to the world. The years leading up to this moment were filled with tension and doubt. Scientific journals were filled with competing models, none of which fully explained the mystery of radiation. The physicist Ludwig Boltzmann had already proposed statistical ideas that hinted at discontinuity, but his theories were controversial and poorly understood. Planck initially rejected Boltzmann's ideas, only to later realize that they held the key to unlocking the secret of energy distribution. Slowly, reluctantly, Planck adopted a statistical view of nature, a view that treated the behavior of atoms not as deterministic, but as governed by probabilities. This was a philosophical leap that went against everything he had once believed. In 1900, after years of struggle, Max Planck presented his solution. He introduced the concept of the quantum of action, now known as Planck's constant, symbolized by h. It was a small number, but its meaning was infinite. It represented the smallest possible unit of energy exchange. With this constant, Planck's equation perfectly matched experimental results across all wavelengths. The scientific community was astonished. For the first time, there was a formula that explained the mystery of blackbody radiation. Yet few realized that this was more than just a mathematical success. It was the birth of quantum physics. The period before this discovery, the era of scientific chaos, is what makes Planck's insight so monumental. The world of science had reached a breaking point, and it was his calm, logical mind that bridged the gap between the old and the new. The chaos before Planck was not merely a time of confusion, it was a time of awakening, when the universe began to reveal its hidden structure. The discovery of quanta would eventually reshape every branch of physics, but in those early days it was a fragile spark, a spark born in the darkness of uncertainty. Planck's work didn't just solve a technical problem, it exposed the limitations of human knowledge. It forced scientists to question everything they thought they knew about matter, energy, and light. It showed that beneath the smooth surface of the classical world lay a realm of strange and unpredictable behavior, a microscopic universe ruled by new laws. The chaos before Planck was, in truth, the necessary silence before the symphony of modern physics began. As the 19th century faded into the 20th, this shift in understanding marked the dawn of a new era. The deterministic world of Newton was giving way to a probabilistic universe, where certainty dissolved into waves of possibility. But before that transformation could take root, the world had to experience the confusion and crisis that preceded it. Planck's discovery did not arise from clarity, it arose from chaos. And that chaos, as history would later show, was the fertile ground from which the quantum revolution would grow. The scientists of that time, though unaware of what was coming, were standing at the edge of one of the greatest transformations in human thought. The darkness before dawn, the disorder before order, the chaos before Planck, this was the crucible that forged the birth of quantum theory. The years surrounding the turn of the 20th century were filled with an invisible tension, an intellectual restlessness that could be felt in every laboratory and lecture hall. The old order of physics, so majestic in its precision, was slowly crumbling under the weight of new discoveries. It was a time when science stood between confidence and confusion, between the comfort of known laws and the terror of the unknown. To understand the greatness of Planck's insight, one must first step into the world that existed before it. The scientific chaos that demanded a savior, even when no one realized one was needed. For generations, scientists had believed that nature could be described completely by the laws of classical mechanics and electromagnetism. The universe, they thought, was a vast machine operating with perfect regularity. Every motion, every vibration, every flash of light could be predicted with enough precision if only one knew the initial conditions. There was no mystery, no uncertainty, only the serene order of mathematical perfection. This vision, born from Newton and expanded by Maxwell, had guided humanity through centuries of discovery. Yet by the late 1800s, cracks began to appear in this perfect structure. The first blow came from thermodynamics, the science of heat and energy. It revealed that not everything could be predicted so easily. Entropy, the measure of disorder, showed that nature had an arrow, a direction toward equilibrium, decay, and irreversibility. Even so, physicists believed that with enough insight, they could still fit these observations into the classical framework. But the problem of blackbody radiation, how objects emit light when heated, refused to be tamed. It was not an exotic question about stars or atoms, it was a simple, everyday phenomenon that no equation could explain. Experimental physicists were meticulously measuring how energy was emitted at different wavelengths from heated metals and carbon filaments. Their instruments revealed a curious pattern. The intensity of radiation increased with wavelength, reached a peak, and then dropped sharply at shorter wavelengths. Classical theories, however, predicted something entirely different. They suggested that as wavelength shortened, the emitted energy should rise without limit. The math led to nonsense, an infinite amount of radiation from any warm object. This was more than a mere miscalculation. It was a breakdown of physics itself. The scientific world was stunned. How could the same laws that explained the motion of planets and the propagation of light fail to describe the glow of a simple furnace? Journals were filled with competing theories. Some tried to modify existing equations, others sought entirely new principles. But every attempt ended the same way: failure. The more the equations were refined, the more glaring their errors became. For the first time in centuries, physics seemed to have encountered a wall it could not climb. Into this turmoil stepped Max Planck, a man who never sought revolution. His nature was cautious, his approach methodical. He was deeply devoted to the concept of order in nature. He believed that the laws of thermodynamics were universal truths, and he devoted much of his career to studying them. When he began investigating the problem of radiation, it was not to overthrow classical physics, but to preserve it. He believed that, with enough patience, reason would triumph over confusion. But what awaited him was a paradox that reason alone could not solve. Planck began by analyzing the work of Wilhelm Wien, who had proposed an empirical formula that matched experimental data for a limited range of frequencies. Wien's law worked well for short wavelengths, but failed for longer ones. Lord Rayleigh and James Jeans offered a different approach based on classical assumptions, but their formula led to the infamous ultraviolet catastrophe. The contradiction between theory and experiment could not have been sharper. Planck found himself standing between two incomplete worlds, one that failed at low frequencies, another that failed at high. If neither was correct, then something far deeper must be wrong. At first, Planck tried to modify Wien's formula mathematically, searching for a middle path that would fit the data across all frequencies. He worked tirelessly, recalculating energy distributions, adjusting constants, and testing every known law. But no matter how elegant his equations appeared, they could not describe the observed results. The failure was not in his mathematics. It was in the very foundation of physics. The assumption that energy could vary continuously, like water flowing in a stream, simply did not fit nature's behavior. Planck faced a choice: abandon his lifelong belief in continuity, or accept that the universe contained something fundamentally discrete. This moment marked one of the most profound turning points in the history of science. In October 1900, Planck introduced a bold hypothesis, not because he wanted to, but because he had no other choice. He suggested that energy could only be emitted or absorbed in fixed amounts, or quanta. These quanta were proportional to the frequency of the radiation, expressed in the simple equation eta cum. Here, h represented a constant, an entirely new universal number that would later be known as Planck's constant. It was a small change in theory, but an enormous leap in understanding. The continuous world of classical physics had given way to a quantized one, where energy came in indivisible packets. At first, the idea seemed absurd. Energy was supposed to flow smoothly, not in jumps. Planck himself was uneasy about his own result. He considered it a mathematical trick, a temporary measure to fix a formula, not a window into the true nature of reality. Yet his equation matched every experimental observation with perfect accuracy. The chaos of unexplained data was suddenly replaced by harmony. However, that harmony came at a philosophical cost. The new theory contradicted centuries of scientific tradition. If energy existed in discrete amounts, what did that mean for light, heat, and matter? Could nature itself be built from discontinuities? Could reality jump from one state to another instead of flowing continuously? These questions disturbed Planck deeply. He was not a man comfortable with speculation, but whether he liked it or not, his equation pointed toward an entirely new understanding of the universe. The scientific chaos that preceded Planck's discovery was, in a sense, the necessary precursor to this transformation. It revealed the limits of human reasoning, the danger of assuming that nature would always conform to our expectations. The failure of classical physics to explain blackbody radiation forced scientists to look beyond the visible, to question the continuity of energy, the smoothness of motion, and the certainty of determinism. It was a time of confusion, but it was also a time of awakening. After Planck presented his results, the scientific community reacted with cautious curiosity. Few understood the full implications of his idea. To most physicists, it seemed like a clever mathematical fit, not a new law of nature. Yet there was something undeniably powerful about it. For the first time, theory and experiment stood in perfect agreement. Slowly, the idea began to take root. In the following years, Albert Einstein extended Planck's concept to explain the photoelectric effect, showing that light itself behaved as a stream of quanta, later called photons. What Planck had introduced to fix one problem had opened the door to an entirely new branch of science, quantum physics. But before all of that, there was the chaos, the uncertainty, the disbelief, the stubborn adherence to classical ideas. It is impossible to appreciate Planck's genius without understanding the intellectual climate of his time. He was a man standing alone between two eras, holding in his hands a formula that no one, not even he, could fully believe. And yet, within that formula lay the seeds of everything that would follow. The atomic model, the uncertainty principle, quantum mechanics, and the technology that defines modern life. The chaos before Planck was not a failure of science, it was its greatest test. It proved that even the most successful theories can reach their limits, that knowledge must evolve beyond comfort. It showed that progress often emerges not from certainty, but from confusion. Planck's discovery was born out of that confusion, out of the willingness to question what had always been assumed true. In the end, his leap into the unknown reshaped not only physics, but the very way humanity perceives reality. When we look back at that era now, we see it not as a time of disorder, but as a moment of transformation. The scientific chaos before Planck was like the turbulence before a star ignites, violent, unstable, but necessary for creation. From the ruins of classical certainty emerged a new vision of the universe, one that acknowledged the strange, quantized rhythm of nature. It was a universe where energy, matter, and even light came in discrete steps, each one a whisper of the cosmic order hidden beneath apparent chaos. Planck himself remained humble about his role. He often said that he had not set out to create quantum theory, only to make sense of existing data. Yet history would remember him as the father of modern physics. The chaos that once surrounded him faded into clarity, replaced by a new understanding of the microcosm. Today we measure energy, time, and motion with instruments that owe their existence to his constant, h. Quantum mechanics governs the behavior of semiconductors, lasers, and the digital devices that define our lives. But behind all that progress lies the story of a man who confronted the limits of knowledge and dared to cross them. The scientific chaos before Planck's discovery was not just a period of confusion. It was the birth cry of a new worldview. It taught scientists that certainty is temporary, that every answer leads to deeper questions. The failure of classical physics was not the end of understanding, but the beginning of something far greater. It was in that confusion, in that darkness, that the light of quantum theory began to shine. And it was Max Planck, calm amid the storm, who captured that light and gave it form. The legacy of that moment still echoes through every discovery that followed. The universe revealed itself to be not a smooth continuum, but a mosaic of tiny, indivisible pieces, each one a fragment of Planck's vision. The chaos that came before him was necessary because it broke the old illusions and forced humanity to look deeper. From that chaos, science was reborn. The birth of the quantum idea was not a moment of sudden revelation, but rather a slow and uncertain awakening, a gradual realization that the universe did not behave according to the neat and continuous laws that humanity had long believed. To understand how this idea was born, we must step into the mind of Max Planck at the dawn of the 20th century, a man whose devotion to order and logic led him to uncover a principle that would shatter both. It was not rebellion that brought him to this discovery, but desperation, persistence, and a willingness to trust the truth even when it defied reason. At the end of the 1800s, physics was standing on a golden pedestal of triumph. Newton's mechanics and Maxwell's electromagnetism seemed to have explained nearly every phenomenon of nature. Scientists believed that the last mysteries would soon be solved, that the great edifice of knowledge was nearly complete. Only a few minor gaps remained, small puzzles that, once answered, would close the book of physics forever. Among these puzzles was one that appeared trivial, the mystery of how objects emit radiation when heated. Yet hidden within that puzzle lay the key to an entirely new universe. When Planck first turned his attention to this problem, he was not expecting revolution. He was a man of method, a scholar who valued mathematical harmony over dramatic leaps. His work was grounded in the principles of thermodynamics, especially the second law, which dealt with entropy, the measure of disorder in a system. He believed that all physical laws could be derived from absolute, deterministic principles. The idea that nature could behave randomly or discontinuously was alien to him. But when he began to study blackbody radiation, that belief began to crumble. Experiments had shown that when a body is heated, it emits radiation across a range of wavelengths. The intensity of this radiation rises with wavelength, reaches a peak, and then falls. The exact shape of this curve depends on the temperature. At low temperatures, the peak is in the infrared region. As the temperature increases, the peak moves toward the visible spectrum, causing the object to glow red, then orange, and finally white-hot. This behavior was known and measured with great accuracy. Yet, no one could explain it theoretically. The best attempts by classical physics produced results that matched only parts of the curve, and disastrously failed at others. The Rayleigh-Jeans law, based on classical electromagnetic theory, predicted that at high frequencies the emitted energy should increase indefinitely. This led to the infamous ultraviolet catastrophe, suggesting that every object should emit infinite energy, something clearly impossible. The discrepancy was not small, it was catastrophic. Nature simply did not follow the predictions of the equations that had once explained the motion of planets and the bending of light. Something fundamental was missing. Planck approached the problem differently. Instead of starting with preconceived assumptions, he began with the data itself, the measured curve of blackbody radiation. His goal was to find a mathematical formula that matched the observed results. He wasn't seeking to redefine the laws of physics, he only wanted an equation that worked. In doing so, he found himself forced into a completely new way of thinking. He first tried to build upon Wien's earlier formula, which worked well for high frequencies, but failed for lower ones. Planck sought a middle ground, a single expression that could unify both ends of the spectrum. He experimented endlessly, testing one mathematical form after another. Then, on the evening of October 19, 1900, while analyzing his latest calculations, something remarkable happened. He found a formula that fit the experimental data perfectly across all wavelengths. The equation was simple and elegant, yet it contained a term that could not be explained by any classical reasoning. It suggested that energy was not continuous but emitted in small discrete packets. At first, Planck resisted this idea. To him, it seemed absurd that energy could come in chunks. The continuous flow of energy was one of the cornerstones of physics. But the data did not lie, and the mathematics demanded this strange quantization. Reluctantly, he accepted it as a necessary assumption. In order to explain the shape of the blackbody curve, he proposed that the energy of an oscillator, an atom or molecule that emits radiation, could only take on specific, discrete values. The amount of energy emitted or absorbed was proportional to the frequency of radiation, described by the equation E, where h was a new fundamental constant of nature. This equation was the birth certificate of quantum theory. It was the moment when humanity first glimpsed the discrete structure of the universe. But at the time, Planck had no idea of its full meaning. He regarded it as a mathematical trick, not a physical law. He even wrote later that he introduced the quantization as an act of desperation. Yet, this act of desperation marked the beginning of a new era, the quantum era. To appreciate the magnitude of this moment, one must understand how revolutionary it was. The entire foundation of classical physics was built on the belief that energy and matter behaved continuously. Light waves were thought to oscillate smoothly, like ripples on water with no interruptions or gaps. The idea that energy could exist only in discrete packets was completely alien. It challenged not only scientific understanding, but also philosophical assumptions about nature's perfection and continuity. Planck's equation introduced a constant that would soon become one of the most important numbers in science. It was incredibly small, about 6.6610 joule seconds, indicating that these packets of energy were minuscule on a human scale. But on the atomic level, They were everything. This constant defined the smallest possible unit of action in the universe. It told scientists that energy changes did not occur smoothly, but in quantum jumps. When Planck presented his results to the German Physical Society on December 14, 1900, the audience did not realize they were witnessing a revolution. Planck himself likely did not realize it either. The announcement was quiet, mathematical, and unassuming. There were no grand declarations, no claims of overthrowing the old order. Yet, within those few lines of mathematics lay the seeds of modern physics. The principles that would later give rise to the atom model, quantum mechanics, and the digital technologies that shape our world. The quantum idea, however, was slow to take root. For several years, it remained largely ignored. Most scientists viewed it as a clever mathematical approximation, useful for calculations but not a reflection of physical reality. Even Planck hesitated to take it literally. He hoped that someday, a more complete classical explanation would replace it. But the universe had other plans. In 1905, Albert Einstein would take Planck's concept further, applying it to explain the photoelectric effect. Einstein proposed that light itself was made up of discrete quanta, or photons. This was the moment when Planck's desperate assumption became a cornerstone of physics. But back in 1900, none of that was yet visible. Planck was alone with his strange new idea, a man standing on the threshold of a new world he could barely see. His quantum hypothesis was both a triumph and a torment. It had solved a problem that had baffled the greatest minds of his generation, but it had done so at the cost of shattering the most cherished beliefs of science. The smooth, predictable universe of Newton was gone, replaced by a world of jumps, discontinuities, and probabilities. Planck's personal feelings about his discovery reveal much about the human side of scientific progress. He was not a revolutionary by nature. He once wrote that he had to force himself to accept the implications of quantization. He continued to hope that the classical laws could someday be reconciled with his results. Yet, as more evidence accumulated, it became clear that his idea was not an approximation, it was reality. The universe was quantized. The birth of the quantum idea was not just a scientific event, it was a philosophical transformation. It changed humanity's understanding of existence itself. The journey to that realization was filled with doubt, resistance, and irony. The man who gave birth to quantum theory never fully embraced its philosophical consequences. He opened the door to a new world, but refused to step through it. That step would be taken by others: Einstein, Bohr, Heisenberg, Schrödinger, who would explore the strange landscape of quanta that Planck had uncovered. Yet, without his cautious courage, without his willingness to follow the truth wherever it led, there would have been no quantum mechanics, no atomic theory, no modern technology. The birth of the quantum idea was not a flash of genius, but the slow dawn of realization, a reluctant acceptance that the universe is not continuous, but built from indivisible pieces. It was the moment when science turned inward, peering into the heart of matter, and discovered that reality was far stranger than imagination. In the glow of heated matter, in the faint light of a blackbody, Max Planck saw the fingerprints of a deeper truth, one that would change the world forever. The idea of the quantum did not come to Max Planck in a sudden flash of revelation. It emerged slowly from years of intellectual struggle, persistence, and an unwavering belief in the harmony of nature. Planck was a man of patience and precision. He belonged to an era of physicists who viewed science not as a playground for imagination, but as a sacred quest for truth. He lived at a time when the laws of thermodynamics and electromagnetism had seemingly explained everything. The Newtonian world appeared complete, the clockwork universe intact, yet in this perfection, Planck saw a whisper of inconsistency, a question hidden in the glow of heat and light. That whisper would soon grow into the roar of a revolution. The story begins in the late 19th century, in the laboratories of Berlin, where Planck was studying the radiation emitted by heated objects. When a metal rod was heated, it glowed red, then orange, then white. Why did it behave this way? Classical physics predicted that as temperature increased, the emitted energy would rise infinitely at shorter wavelengths. But experiments showed something different. Nature refused infinity. There was a limit. The theoretical framework that explained so much of the macroscopic world failed miserably in the microscopic domain. Planck was not seeking to create a new science, he was trying to fix the old one. But as he dug deeper, he realized that the laws of nature were whispering an unfamiliar language, one that defied the smooth continuity of classical thought. He began to examine the mathematical patterns of the radiation curve, desperate to find an equation that matched reality. For months, he tested formula after formula, guided by intuition rather than ideology. Then, in a moment of clarity born from exhaustion, Planck noticed a pattern in how energy must be distributed among the atomic oscillators that produced light. He realized that energy could not vary continuously. It must come in steps, in discrete packets proportional to the frequency of radiation. In simple terms, light was not a flowing stream, but a series of drops. It was a radical departure from everything physics stood for. To the deterministic thinkers of his time, it was madness. But to Planck, it was the only way to make sense of the data. The discovery of the quantum constant, denoted by h, marked a turning point in science. It was a value so small that it revealed a hidden scale of nature, an invisible structure beneath reality itself. Planck's equation, E/n, became a doorway to this microscopic world. Each quantum represented a unit of action, the smallest possible amount of energy exchange between matter and radiation. Though Planck himself viewed it as a mathematical necessity rather than a physical truth, the implications were profound. For the first time, energy, a seemingly continuous quantity, was shown to be fundamentally discrete. The universe, once imagined as smooth and infinite in its divisibility, was now composed of indivisible packets of action. Yet, even as the world around him failed to grasp the magnitude of his discovery, Planck remained cautious. He did not proclaim a revolution, he called it a hypothesis. He feared that the scientific community, steeped in centuries of deterministic faith, would reject the idea outright. And indeed they did. Many of his contemporaries saw the quantum as a clever trick to fit experimental data, not as a glimpse into a new reality. But Planck's reasoning was not built on speculation. It was grounded in observation, logic, and mathematical precision. In the silence of his study, beneath the glow of an oil lamp, he recalculated and rechecked every line of his work, every assumption. The results always pointed to the same truth: energy came in quanta. As the 20th century dawned, Planck's idea began to spread quietly through scientific circles. Young physicists, open-minded and daring, found in it a new path. Among them was Albert Einstein, who saw beyond Planck's caution. Einstein realized that if energy was quantized, then light itself might consist of individual packets, photons. This bold leap extended Planck's concept from abstract radiation to tangible reality. It explained phenomena that classical physics could not, such as the photoelectric effect. Though Planck himself hesitated to follow Einstein's interpretation, the seeds had been sown. The birth of the quantum was no longer a hidden whisper. It was the first cry of a new science. In the years that followed, the implications of Planck's work began to unfold like the pages of a cosmic manuscript. The quantum theory offered explanations for atomic behavior, chemical reactions, and even the stability of matter itself. What had once been invisible now had structure. What had once been mysterious now had meaning. The universe, it seemed, was built not of continuous waves but of pulses, tiny bursts of existence governed by the constant h. Planck had unknowingly cracked open the code of creation. His discovery would become the foundation upon which all modern physics was built. But for Planck, the personal journey was one of humility and quiet awe. He never saw himself as a revolutionary. To him, science was not about overthrowing ideas, but about finding the deeper order hidden within chaos. Even after receiving the Nobel Prize in 1918, he maintained that his theory was one act of desperation, a last attempt to fit theory to experiment. Yet, history would remember him as the man who opened humanity's eyes to a deeper reality, a world where certainty dissolved into probability, and where the building blocks of existence danced in discrete rhythms of energy. Planck's birth of the quantum was more than a scientific milestone, it was a philosophical awakening. It shattered the illusion that nature was smooth and predictable. It revealed that beneath the visible lies a world of jumps, leaps, and discontinuities, a world where the smallest events define the greatest truths. This idea forever altered the course of human thought. It taught scientists to look not for the continuous, but for the discrete, not for the obvious, but for the hidden. The quantum became a new way of seeing, of questioning, of understanding. In every photon that strikes a camera sensor, in every laser beam that cuts through steel, in every transistor that powers our devices, the legacy of that discovery lives on. It is a legacy born not from ambition, but from curiosity and precision. Max Planck, the reluctant revolutionary, had unknowingly set the world on a path toward the quantum age. His theory of elementary quanta did more than solve a problem in radiation. It transformed our understanding of energy, matter, and existence itself. The birth of the quantum idea was the dawn of modern physics, the moment when humanity first glimpsed the architecture of reality. From that moment on, nothing would ever be the same. The world of the infinitely small had opened its doors, and through them walked a man who sought only to understand light, but in doing so, illuminated the universe. In the heart of 19th century physics, one problem haunted every scientist who sought to understand the nature of heat and light: the mystery of blackbody radiation. It was a simple question that refused to yield a simple answer. When an object was heated, it began to glow, red at first, then orange, then white as the temperature rose. Yet no existing theory could explain why. Every law of classical physics, every equation derived from centuries of study, broke apart when faced with this puzzle. The brightest minds of the age, Kirchhoff, Wien, Rayleigh, and others, all tried to capture this behavior in mathematical form. But no matter how hard they tried, something was always off. The universe seemed to obey a rule no one could see, a law beyond the reach of human intuition. Max Planck entered this world of confusion not as a rebel, but as a scholar seeking order. He was a man who revered the beauty of established laws, the harmony of mathematics, and the certainty of logic. When he first encountered the blackbody problem, he did not intend to revolutionize physics. He merely wanted to find a consistent explanation that fit the data. His approach was calm and deliberate, a mathematical investigation guided by reason. He began by analyzing the experimental curves, showing how intensity of radiation varied with wavelength at different temperatures. The data revealed a perfect pattern, smooth, continuous, and precise, yet it refused to conform to any theoretical model of the time. Classical physics predicted that as the wavelength decreased, the emitted energy should increase without bound. But reality disagreed. The experimental curve peaked at a certain point and then dropped sharply. Something profound was missing from the picture. Planck's mind worked like that of a sculptor, chiseling away each unnecessary assumption until only truth remained. He began by examining the work of Wilhelm Wien, who had proposed a formula that matched experimental results at shorter wavelengths, but failed at longer ones. Planck admired Wien's efforts, but knew that the formula lacked a solid theoretical foundation. He turned his attention to Lord Rayleigh's classical explanation derived from electromagnetic theory. That, too, fell apart. It predicted that energy would become infinite as wavelengths grew shorter, leading to what physicists later called the ultraviolet catastrophe. Planck was trapped between two worlds, one that worked for short wavelengths and another for long, but none that captured the whole truth. For a time, he tried to bridge the gap using the old laws of thermodynamics and electromagnetic theory, adjusting parameters, testing equations, and seeking patterns. But the problem refused to yield. The radiation spectrum, like a riddle from nature, remained unsolved. And then, driven by desperation more than confidence, Planck tried something unthinkable. He abandoned the assumption that energy was continuous. He imagined that the atoms inside the heated body did not exchange energy smoothly, but in small, discrete amounts. It was a purely mathematical step at first, an adjustment to make his equations fit the data. But it worked. With this radical assumption, Planck derived a formula that perfectly matched the observed spectrum of blackbody radiation. The formula became known as Planck's radiation law, a triumph of mathematical precision and physical insight. Yet when Planck examined the meaning of what he had done, he realized he had crossed into unknown territory. His assumption that energy was quantized, existing only in multiples of a smallest unit, had no precedent in physics. The idea was so alien to classical thought that Planck himself could barely accept it. In his private notes, he called it an act of desperation. But this act of desperation would soon reshape the very foundations of science. To explain his new formula, Planck introduced a new constant, now known as Planck's constant, denoted by h. This constant defined the size of the energy packets, or quanta, that could be exchanged between matter and radiation. Its value was unimaginably small, but its implications were vast. It suggested that nature operated on a scale beyond human perception, a world where the rules of classical physics dissolved into something new and mysterious. At first, Planck believed this quantization applied only to the processes of emission and absorption, not to the energy of light itself. But even this cautious interpretation was revolutionary. For the first time, the continuity of energy, a cornerstone of physics, had been broken. Planck's struggle to explain blackbody radiation revealed something profound about the scientific process itself. Discovery is rarely a single moment of enlightenment. It is often the result of persistence, humility, and the courage to question what others accept as truth. Planck's path was not smooth. He faced criticism, confusion, and self-doubt. Many of his contemporaries could not grasp what his theory implied, and Planck himself avoided proclaiming it as a new physical law. Yet behind his quiet demeanor was a man of deep conviction. He trusted the mathematics, even if its meaning was unclear. He once said that he had fitted the empirical formula at all costs, knowing full well that it might defy conventional understanding. In his lectures, Planck often spoke softly, with precision and calm authority. But when he described the radiation problem, his tone carried a rare excitement. He knew that something extraordinary had been uncovered. Even if he could not yet define it, he sensed that his work had opened a door to a deeper level of nature's structure. The old world of classical physics, built on continuity and determinism, had been cracked open by a single equation. Planck did not yet realize it, but he had given birth to the quantum age. The implications of Planck's work extended far beyond his original intent. His radiation law not only solved the blackbody problem, but also hinted at a fundamental discreteness in all physical processes. This concept would soon be expanded by others, Einstein, Bohr, Heisenberg, and Schrödinger, who would transform it into a full-fledged theory of quantum mechanics. But it all began with that one puzzle, that one moment of struggle between theory and observation. The blackbody radiation problem was more than a technical difficulty. It was the fault line between two eras of science. Planck's perseverance through this problem also revealed his character, a man devoted not to fame or revolution, but to truth. He often said that science advances, funeral by funeral, meaning that old ideas give way only when new generations embrace the unknown. He was, in many ways, a bridge between two worlds, the world of classical certainty and the world of quantum uncertainty. His discovery marked the last great triumph of 19th-century physics and the first great breakthrough of the 20th. By solving the blackbody problem, Planck not only resolved a scientific paradox but also unlocked a new vision of the cosmos. His radiation law became the first mathematical description of the quantum world, the invisible realm beneath atoms and molecules. Through it, humanity gained its first glimpse of a universe made not of continuous waves but of tiny quanta, flickers of energy, pulses of existence that defined the rhythm of creation. Planck's struggle had not merely explained how objects glow when heated, it had revealed how energy itself behaves at the most fundamental level. The story of that struggle is a reminder that even the most stubborn mysteries of nature can be solved through persistence and imagination. Planck's Blackbody problem was not just a chapter in the history of physics. It was the turning point at which humanity first touched the fabric of reality itself. The glow of a heated object, once a simple curiosity, became the key to understanding the hidden architecture of the universe. And behind that revelation stood a man who sought order, but found revolution. Max Planck's journey to explain blackbody radiation stands as one of the greatest testaments to human intellect, the moment when reason, mathematics, and intuition converged to reveal the birth of the quantum world. Planck's struggle with the problem of blackbody radiation did not end with his famous equation. In many ways, that was only the beginning of his intellectual battle, a journey from disbelief to gradual acceptance of the very idea he had uncovered. After publishing his results, Planck began to realize the depth of what his equations implied. Energy, he had found, could not vary continuously, but only in steps, in discrete packets. To Planck, this was deeply unsettling. His entire scientific upbringing was grounded in the belief that nature was smooth and continuous, not jagged and fragmented. The idea that something as fundamental as energy came in indivisible units was almost philosophical heresy. And yet, no matter how he reworked the equations, the result stood firm. The mathematics was correct. The data agreed. Reality had spoken. In those early years after 1900, Planck's nights were filled with quiet contemplation. He would sit in his study, surrounded by papers, rechecking each line of derivation, searching for a mistake that did not exist. He had not intended to create a new physics. He only wanted to describe the radiation of heat. Yet he had stumbled upon something that defied the very principles that had guided science since Isaac Newton. It was as if he had peeled back a layer of the universe and glimpsed a structure that classical physics could not explain. Every attempt to interpret his own theory within the framework of old ideas led to contradictions. The realization grew heavier in his mind. The foundation of science itself was shifting. Planck's initial reluctance to accept the physical reality of quanta reflected not weakness, but intellectual honesty. He did not claim to understand more than he did. He once described himself as a reluctant revolutionary. To him, the quantization of energy was a mathematical trick, a convenient fiction to make the equations work. But as experiments continued to confirm his predictions, that fiction began to take on the weight of truth. Other scientists noticed too. Within a few years, Albert Einstein reinterpreted Planck's quantum hypothesis to explain the photoelectric effect, showing that light itself was made up of particles, which later came to be known as photons. Planck initially disagreed with Einstein's bold leap, yet deep down he recognized the same pattern. Nature was quantized not only in energy, but in light itself. Slowly, the idea he had once treated as a last resort began to feel like a revelation. The struggle to explain blackbody radiation had opened a door into an entirely new domain of reality. Behind that door lay the quantum world, a place where certainty dissolved into probability, where energy moved not continuously but in jumps, and where the familiar laws of physics were rewritten. Planck, ever the cautious thinker, approached this revelation with reverence. He believed that even in this new and mysterious world, the underlying harmony of the universe remained intact. To him, the quantum was not a contradiction to nature's order, but a deeper expression of it. He saw beauty in the idea that even at its smallest scales, the universe followed rules, strange and unfamiliar, yes, but rules nonetheless. As years passed, Planck's law became one of the cornerstones of modern physics. Its implications stretched far beyond the radiation of heat. It provided a key to understanding the behavior of atoms and molecules, the emission of light from stars, and even the structure of matter itself. What began as a problem of glowing metal had grown into a universal principle. Planck's quantum hypothesis became the seed from which all of quantum mechanics would grow. Scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would later take that seed and build an entirely new vision of the universe. One that described not just light and heat, but all of existence in terms of probability and quantization. In retrospect, Planck's struggle with blackbody radiation seems almost poetic, a story of persistence against impossibility. He had followed reason to a place where reason itself had to evolve. The equations he derived were like messages from the universe, written in a code that only time could fully decipher. And though Planck did not yet grasp the full scope of his discovery, he sensed that he had touched something profound. In his later writings, he reflected on the mystery of his own journey, saying that to bring about a theoretical interpretation at any cost, no matter how high, that cost was nothing less than the transformation of physics itself. There was something deeply human about Planck's hesitation and his eventual acceptance. His struggle mirrored the journey of science itself, the painful yet beautiful process of letting go of old certainties to embrace a greater truth. In Planck's story, one can see the moment when the universe revealed its dual nature, when light became both wave and particle, when matter lost its solidity and became a web of probabilities. All of it began with one man's attempt to solve a problem that others had given up on. His quiet determination turned failure into discovery. His patience transformed confusion into clarity. Even as the 20th century unfolded and the quantum theory blossomed into a vast and complex field, Planck remained humble about his role. He never claimed to have foreseen where it would lead. Yet his contribution was monumental. Without Planck's solution to the blackbody problem, there would be no understanding of atomic structure, no lasers, no computers, and no modern electronics and no quantum technologies. The entire digital world of today rests on that single, revolutionary idea, that energy, at its core, is quantized. Looking back, it is astonishing to realize that this monumental shift in human understanding began with something as ordinary as the glow of a heated object. The blackbody problem had seemed trivial at first, but it held the key to unlocking the architecture of the universe. Planck's persistence turned that mystery into a revelation. He did not seek to overthrow classical physics, but his equations did exactly that. They showed that beneath the smooth surface of the world lay a hidden rhythm, a discrete pulse that governed everything from the vibration of atoms to the light of stars. By the end of his life, Planck had come to see his discovery as part of something greater, a cosmic order that was both mathematical and spiritual. He believed that the laws of physics were not mere inventions of the human mind, but reflections of a deeper truth woven into the fabric of existence. His quantum theory, born out of desperation, had become the foundation of a new worldview, one that revealed both the limits and the wonder of human knowledge. Thus, Planck's struggle to explain blackbody radiation stands as one of the greatest intellectual battles in history. It was not a fight against nature, but a dialogue with it, a conversation conducted through mathematics, persistence, and imagination. In confronting the mystery of heat and light, Planck discovered not only the quantum, but the humility of science itself, that every answer opens new questions, and that even the smallest number, the constant h, can change the course of human thought forever. In the quiet glow of his Berlin study, surrounded by papers and equations, Max Planck had unknowingly rewritten the language of the universe. His discovery was not loud or dramatic. It was born from silence, precision, and faith in reason. Yet it shook science to its core. The blackbody radiation problem that once defied explanation became the gateway to a new era, a quantum world where certainty fades and mystery reigns. Through that struggle, Planck revealed one of the most profound truths of all, that even in chaos, the universe speaks a language of order, and that the pursuit of understanding, however difficult, is the truest light of human progress. When Max Planck introduced his revolutionary idea that energy existed in discrete packets called quanta, He also gave birth to one of the most fundamental constants in physics, Planck's constant, symbolized by the letter Lr. This seemingly small number, approximately 6.626 × 10 joule seconds, marked a turning point in human understanding of the universe. It was not just a value to plug into equations, it was a bridge between the known and the unknown, the visible and the invisible. It represented the smallest possible unit of action in nature, the scale at which the classical world of smooth continuity breaks down and the quantum world begins. Before Planck's discovery, scientists believed energy could change in any amount, smoothly and continuously, like water flowing from a tap. Planck's work shattered that view. He proposed that energy could only change in small, indivisible steps, multiples of Rex times the frequency of the radiation. This meant that light, heat, and all forms of electromagnetic radiation could not be emitted or absorbed arbitrarily. They were governed by a universal rhythm defined by this constant. It was as if nature had set a minimum beat to the cosmic symphony, and no process could move to a smaller note. The equation EF became the cornerstone of quantum theory. In it, EF represents the energy of a quantum, R nu represents its frequency, and HA is Planck's constant, the proportional link that unites energy and vibration. This idea might seem simple, but it overturned centuries of belief. It showed that even light, long thought to be a continuous wave, carried energy in discrete chunks. That realization transformed physics from a study of smooth motion into an exploration of the granular structure of reality itself. At first, many physicists, including Planck himself, struggled to grasp the full meaning of EF. It was just a number, yet it hinted at a mysterious boundary, an invisible line between the familiar world of classical mechanics and the strange, unpredictable world of quantum mechanics. When the value of Is was inserted into calculations, it revealed that the scale of quantum effects was unimaginably small, far below the threshold of everyday experience. That was why the laws of classical physics worked so well in the macroscopic world, but failed at atomic and subatomic scales. The universe had two languages, and Iser was the translator between them. The beauty of Planck's constant lay in its universality. It appeared not only in the study of radiation, but in every phenomenon involving the smallest particles of nature. From the orbits of electrons in atoms to the emission of light in stars, from the behavior of semiconductors to the operation of lasers, arcs governed all. Its discovery allowed scientists like Einstein, Bohr, and Schrödinger to build the mathematical foundations of quantum mechanics. Einstein used it to explain the photoelectric effect, proving that light could behave as both particle and wave. Bohr applied it to describe the energy levels of hydrogen atoms, showing that electrons could occupy only specific orbits. Schrödinger used it to write his wave equation, the very heart of quantum theory. Without F, none of these achievements would have been possible. What makes Planck's constant even more remarkable is its philosophical depth. It suggests that there is a fundamental granularity to reality, that nature, at its deepest level, is not continuous but quantized. Every vibration, every flicker of energy, every shift in the atomic world happens in finite steps, never in between. This defied the human intuition shaped by everyday experiences, where motion and change appear smooth. The discovery of Achar's forced science to accept that the universe operates according to principles that cannot always be visualized or predicted with certainty. It was the first hint of the quantum strangeness that would later define modern physics. Over time, Planck's constant became more than a physical parameter. It became a symbol of a new worldview. It defined the scale at which the classical laws of Newton give way to the probabilistic nature of the quantum realm. In this new world, particles could exist in multiple states at once, and observation itself could alter outcomes. All of this stemmed from the quantization that Skepticism introduced. Every jump of an electron, every photon of light, every transition of energy in the cosmos follows this tiny but universal rule. Today, Planck's constant stands at the very foundation of modern science. It defines the unit of action in the universe, sets the scale for quantum effects, and even plays a role in defining the kilogram, one of the base units of the international system of measurements. It connects time, energy, and frequency into a single framework. It is the quiet rhythm of the cosmos, governing processes too small for the human eye, but essential to everything that exists. When Planck first calculated h-rare, he had no idea it would become one of the most important constants in physics. He saw it only as a necessary mathematical device to make his radiation formula fit experimental data. Yet in doing so, he had discovered the fingerprint of the quantum world. His constant revealed that the universe, at its most fundamental level, was not a smooth ocean but a sea of tiny ripples, each carrying a fixed and finite amount of energy. That revelation changed everything. It led to quantum mechanics, quantum chemistry, quantum computing, and our understanding of light, matter, and energy. It transformed not just science but philosophy, forcing humanity to rethink the nature of reality itself. The revolutionary constant H was more than a number, it was a symbol of a new era, a reminder that even the smallest thing in the universe can hold the greatest meaning. Max Planck's discovery of this constant became the foundation upon which modern physics stands, the silent heartbeat of a quantum world that still continues to astonish us today. When Max Planck first proposed his theory of energy quanta, the scientific world did not immediately embrace it. The idea that energy was not continuous but came in small, discrete packets was too radical for most physicists to accept. For centuries, science had been built upon the smooth, predictable laws of Newton and Maxwell, laws that seemed to describe every motion in the universe. The concept of quantized energy broke this long-standing harmony. Planck himself was deeply cautious about his discovery. He believed his formula worked mathematically, but doubted that nature truly behaved that way. His peers shared his skepticism. They could not accept that the elegant continuity of physics might be replaced by a world of sudden jumps and invisible steps. Thus began one of the most challenging periods in scientific history, the skeptical beginning of quantum theory. When Planck published his findings in 1900, most physicists viewed them as an ingenious mathematical trick rather than a physical truth. They saw no reason to abandon classical physics, which had explained everything from planetary motion to electromagnetism. The idea of quantization seemed unnecessary and even absurd. Energy, they argued, was a continuous flow, not a sequence of pulses. Planck's theory, they said, was a convenient adjustment, not a revolution. But the problem was that no other explanation worked. The Blackbody radiation curves matched Planck's equation perfectly, while classical formulas led to impossible infinities. Nature was hinting that Planck might be right, even if logic resisted. In the early years of the 20th century, the tension between classical certainty and quantum possibility grew. Planck's discovery lingered in the background of scientific discussion, a curiosity rather than a breakthrough. Then, in 1905, Albert Einstein stepped into the story, building on Planck's idea. Einstein proposed that light itself was made of quanta, tiny packets of energy he called light quanta, later known as photons. This bold interpretation explained the mysterious photoelectric effect in which light striking a metal surface could eject electrons. Classical theory said that brighter light should always release more energy, but experiments showed that only light above a certain frequency could do so. Einstein's explanation fit perfectly with Planck's quantization. Each photon carried energy proportional to its frequency, following the same equation, E.A. Einstein's insight gave physical meaning to Planck's formula, turning it from a mathematical fit into a profound statement about the nature of light itself. Yet even then, skepticism persisted. Planck himself hesitated to accept Einstein's photon theory. To him, light was still a continuous wave, not a stream of particles. He admired Einstein's brilliance but believed his interpretation went too far. Other scientists, including the great Lord Rayleigh and James Jeans, clung tightly to classical theories. The idea of photons seemed almost mystical, a step backward to a pre-wave understanding of light. It was a paradox. Planck's mathematics had opened the door to quantum reality, but even he could not yet walk through it. For several years, the quantum idea existed in a twilight zone, supported by experiment but resisted by belief. It took a generation of young, bold thinkers to finally embrace it. Niels Bohr, inspired by Planck and Einstein, applied quantization to the structure of atoms, showing that electrons could occupy only specific energy levels. When an electron jumped between levels, it emitted or absorbed a photon of fixed energy, again following eta. This model explained the colors of light emitted by different elements, something classical physics could never do. Suddenly, Planck's constant was no longer an isolated curiosity, it was the key to understanding the building blocks of matter. Still, resistance lingered. Many older scientists found quantum theory unsettling because it introduced limits to knowledge and predictability. The world they had known was orderly and deterministic, every effect had a clear cause. The quantum world, by contrast, seemed unpredictable, filled with probabilities rather than certainties. The skeptical voices argued that this could not be the ultimate truth. Yet, as experiments accumulated, from atomic spectra to the photoelectric effect, and later to the Compton scattering of X-rays, quantum theory proved correct every time. Slowly, the tide of skepticism began to turn. Planck watched this transformation with quiet satisfaction. Though he had once doubted his own creation, he lived long enough to see it reshape science. The very constant he had introduced out of mathematical necessity became a universal symbol of physical reality. The skeptics, one by one, accepted that the quantum world was real. Einstein's early work on photons earned him the Nobel Prize in 1921, not for relativity but for his explanation of the photoelectric effect. A victory for the quantum idea born from Planck's work. The skeptical beginning of quantum theory serves as a reminder of how deeply new ideas can challenge human understanding. Even the greatest minds struggle to accept truths that contradict their experience. Planck's discovery demanded not only a new mathematics, but a new philosophy of nature. It asked scientists to imagine a world where energy and matter existed in discrete forms, where certainty gave way to probability, and where the observer could never be completely detached from the observed. This revolution in thought did not come overnight. It took decades of debate, proof, and persistence. But out of that skepticism grew a new science that would redefine the 20th century. Quantum mechanics emerged from the doubts and arguments that followed Planck's discovery. What began as a controversial idea became the foundation of modern physics, chemistry, and technology. Max Planck's theory, once met with disbelief, became the cornerstone of our understanding of the universe. The skepticism that once surrounded it is now remembered as part of its triumph. In the end, the resistance of the scientific community only highlights how powerful the discovery truly was. It forced humanity to see the world in a way it had never imagined before. The skeptical beginning of quantum theory was not a sign of failure. It was the growing pain of a new era of science, one that continues to expand our view of reality to this day. The rise of quantum theory after Max Planck's discovery marked a new dawn in the history of science, a revolution that forever changed our understanding of reality. Once dismissed as a mathematical trick, Planck's constant, the mysterious h, became the cornerstone of a vast and intricate framework that reshaped physics, chemistry, and even philosophy. What began as an attempt to solve a simple problem about radiation grew into a complete redefinition of how the universe operates on its smallest scales. The legacy of this theory is nothing short of extraordinary. It gave birth to the modern world as we know it. As the 20th century unfolded, Planck's quantum concept inspired a new generation of scientists. Niels Bohr applied quantization to his atomic model, showing that electrons revolve around the nucleus in discrete orbits rather than in continuous paths. When electrons jumped from one orbit to another, they emitted or absorbed quanta of light with energies determined by Planck's equation, E·h nu. This simple yet profound idea explained atomic spectra, the fingerprints of elements, and confirmed that Planck's constant governed the structure of atoms themselves. Quantum theory had found its home within the atom, unlocking secrets that classical physics could never reach. Soon after, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built the formal mathematical foundations of quantum mechanics. They developed equations that described not only light, but the very behavior of matter. Heisenberg's uncertainty principle revealed that we could never know both the position and momentum of a particle with perfect accuracy, a direct consequence of the quantum nature of reality. Schrödinger's wave equation showed that particles could behave like waves, and waves could behave like particles, blurring the boundary between what was once thought separate. Dirac's work merged quantum theory with relativity, predicting the existence of antimatter. Each step carried Planck's idea further, demonstrating that his constant h was not just a mathematical convenience, but a fundamental fingerprint of nature itself. The technological impact of these discoveries was immense. Quantum theory laid the foundation for the invention of the transistor, the essential component of all modern electronics. Without it, computers, smartphones, and digital communication would not exist. Quantum mechanics also made possible the development of lasers, semiconductors, and nuclear energy. The once abstract theory that emerged from the study of blackbody radiation became the driving force behind the modern technological age. Every time we use a GPS satellite, make a video call, or power a computer chip, we are relying on principles that trace directly back to Planck's quantum idea. Beyond technology, quantum mechanics transformed the way humanity perceives the universe. It revealed that reality, at its most fundamental level, is governed not by certainty but by probability. The deterministic vision of Newton gave way to a world where chance and uncertainty play central roles. Einstein famously resisted this notion, saying, "God does not play dice with the universe." But experiments repeatedly proved that quantum probabilities were real and measurable. Later discoveries, such as quantum entanglement and superposition, showed that particles could exist in multiple states at once and remain connected across vast distances. What was once thought impossible became essential to our understanding of how the cosmos operates. Quantum theory also bridged the gap between the smallest and largest scales of existence. It explained the behavior of subatomic particles, but its influence extended to stars and galaxies. Nuclear fusion, the process that powers the sun and all stars, can only be understood through quantum tunneling, a process where particles pass through barriers they seemingly shouldn't cross. Even the birth of the universe, in the Big Bang, is described in quantum terms. Planck's constant defines the smallest measurable scales of space and time, known as the Planck length and Planck time, boundaries beyond which our current physics cannot yet explain. The philosophical implications were equally profound. Quantum mechanics challenged the very nature of observation and reality. It suggested that the act of measurement influences the outcome, that reality may not exist independently of observation in the way classical physics assumed. This idea fascinated and unsettled scientists and philosophers alike. It raised deep questions about free will, determinism, and the limits of human knowledge. In many ways, Planck's discovery did not just change science, it changed the way we think about existence itself. Max Planck's legacy is now woven into every aspect of modern physics. His name lives on in the Planck units, which define the natural scales of the universe, and in the Planck satellite, which map the cosmic microwave background. The afterglow of the Big Bang. His discovery opened the door to quantum field theory, particle physics, and the search for a unified theory that connects gravity with quantum mechanics. From the microchip to the stars, from the structure of atoms to the birth of the cosmos, Planck's quantum has become the language of nature. More than a century later, the impact of Planck's theory continues to expand. Today's quantum technologies, such as quantum computers, quantum communication, and quantum cryptography, are direct descendants of his original idea. Scientists are now building machines that use quantum states to process information at unimaginable speeds, ushering in what many call the second quantum revolution. The same mysterious principles that once puzzled Planck are now being harnessed to transform the future. In the end, the story of Planck's discovery is not just the tale of a scientific breakthrough. It is the story of human curiosity and courage. Planck dared to question the most fundamental assumptions of his time. Though he began his journey reluctantly, he opened a pathway that others followed to the very heart of reality. His theory of elementary quanta revealed that the universe is built not from continuous waves, but from tiny, indivisible packets of energy. Simple, elegant, and profoundly mysterious. From skepticism to triumph, from mathematics to philosophy, from atoms to galaxies, Planck's idea continues to shape every corner of modern science. His discovery did not just shake the foundations of physics, it redefined them, proving that even the smallest constant can change the course of human understanding forever. As the 20th century progressed, the legacy of Max Planck's theory of elementary quanta spread far beyond physics, transforming every branch of science and technology, and even reshaping how humanity perceives its place in the universe. What began as an attempt to solve the puzzle of blackbody radiation became the seed of an entirely new worldview. A worldview that redefined energy, matter, and reality itself. The story of this transformation is not merely about equations or discoveries, it is about the evolution of human thought, the courage to question what seemed absolute, and the vision to embrace uncertainty as a fundamental truth of nature. Planck's idea became a bridge between the visible and the invisible, the known and the unknown, leading to the dawn of the modern scientific age. The influence of Planck's quantum concept reached into every corner of science. In chemistry, it explained why atoms form bonds and why materials emit light in specific colors. In biology, it illuminated the processes of photosynthesis and vision, showing how photons trigger reactions within living cells. In astronomy, quantum physics became essential for understanding the behavior of stars, black holes, and the earliest moments of the universe. Even the vast cosmos, stretching across billions of light years, obeyed the same tiny quantum rules that govern subatomic particles. The discovery that the same constant, h, applied universally revealed a profound unity in nature, from the smallest quantum to the grandest galaxy. Everything followed the same mysterious pattern of quantized energy. Quantum mechanics also redefined technology in ways that Planck could never have imagined. The invention of transistors and semiconductors led to computers and the digital revolution. Lasers based on quantum principles transformed medicine, communication, and industry. Magnetic resonance imaging, MRI, revolutionized medical diagnostics, while atomic clocks, using quantum transitions, gave birth to precise global positioning systems. The invisible quantum world became the engine of modern civilization. Every piece of modern technology, from smartphones to satellites, owes its existence to the insights that began with Planck's equation, eton A. What once seemed an abstract mathematical curiosity became the foundation of the technological world we live in today. But quantum theory did not stop there. As scientists delved deeper, they encountered even stranger phenomena that challenged all intuition. Quantum entanglement revealed that two particles could remain connected, instantly affecting each other across any distance, a phenomenon Einstein himself called spooky action at a distance. Later experiments confirmed that this was real, showing that information could be correlated beyond classical limits. This discovery laid the groundwork for quantum communication and the emerging field of quantum computing, where information is stored and processed using the strange properties of qubits, units that can exist in multiple states simultaneously. These advances mark the beginning of what scientists call the second quantum revolution, one that promises to reshape the future just as dramatically as the first. The philosophical consequences of Planck's discovery are equally deep. Quantum theory shattered the old assumption that the universe operates in a perfectly predictable, mechanical way. It replaced certainty with probability, determinism with possibility. The observer became part of the system, influencing outcomes simply by the act of measurement. This raised profound questions: is reality objective, or does it depend on observation? Does the universe exist in definite states before we measure them? Such questions blurred the line between science and philosophy, forcing humanity to reconsider its understanding of truth and existence. Planck's discovery, though born from physics, evolved into a meditation on the very nature of reality. Even today, physicists continue to explore the boundaries of quantum theory. Quantum field theory, an extension of Planck's work, describes how particles arise as excitations of underlying fields that permeate all space. The standard model of particle physics, which explains all known forces except gravity, is built entirely on quantum principles. Yet mysteries remain. Gravity, the force that shapes the cosmos, still resists full integration into quantum theory. Scientists dream of a theory of everything that will unite the quantum and cosmic realms, a dream that began with Planck's constant over a century ago. Max Planck's own life reflected the same quiet persistence and humility that defined his science. He never sought fame or revolution, yet his discovery transformed human understanding more than any other in modern times. Even in the face of skepticism, he remained devoted to truth. When others doubted the meaning of his constant, he continued refining his work, guided by the belief that nature's laws, no matter how strange, are ultimately harmonious. That belief proved prophetic. Every advance in physics since his time has confirmed that his constant, h, is one of the most fundamental quantities in the universe, a key that unlocks both matter and energy, light and time. Today, more than a century after his discovery, Planck's quantum theory continues to inspire wonder and exploration. Quantum computers promise to revolutionize information processing. Quantum encryption could make communication unbreakable. Quantum sensors may soon detect the faintest ripples of gravity or changes in space, time itself. Each of these innovations traces its origin back to Planck's bold idea that energy is quantized, that the universe at its core is built from tiny, discrete pulses of reality. The story of Planck's theory is a story of human awakening, how one simple equation revealed the hidden structure of existence. It teaches that progress often begins in doubt, that great discoveries demand the courage to challenge tradition, and that truth can emerge from the smallest, most unexpected places. Planck's discovery shook science because it forced humanity to look deeper, to see the universe not as a smooth continuum, but as a dance of quanta, vibrating with the rhythm of creation itself. In the end, Max Planck's theory of elementary quanta stands as one of the greatest milestones in human history. It bridged the visible and invisible worlds, linking the motion of galaxies to the flicker of atoms. It gave birth to quantum mechanics, which in turn gave rise to the technologies, philosophies, and possibilities that define our modern age. The discovery that once seemed impossible became the foundation of everything we now understand about reality. Planck's idea did not merely change physics. It changed the way we see the universe, and the way we see ourselves within it. His quanta, the smallest steps of energy, became the greatest leap in human knowledge.